thanks for staying so late on Friday. This is joint work with Daniel Schoepe and Andrei Sabelfeld from Chalmers University, Musard Balliu from KTH, and my advisor Michael Pradel from University of Stuttgart. And the main aspect we want to analyze in this work is basically the trade-off in building more advanced program analysis and considering more and more advanced types of implicit information flows. Let's start with this simple JavaScript example. We have a password that we concatenate with a constant, a got_it flag that we initialize on false. We have another variable known password, and based on the conditional, like an equality on the padded password, we set the flag on true and we copy the password in the known password. Finally, we send this flag to the sink. And the main question we ask in applying program analysis to security very often is there a flow from a specific source, in this case password, to the sink? But this depends on what kind of information flow or what kind of program analysis you're building. Are you just tracking explicit flows? Then you're building a taint analysis. Observable tracking is interested in specific types of implicit flow, and there are even more advanced information flow control techniques. I will now briefly show how each of them works by showing on this simple example how the analysis reasons about the sources sinks relationship. So first, taint analysis, as I said, only tracks explicit information flows or data flows. It starts with the password. On the explicit flow there, it propagates the taint to the padded password. Then it sees that, oh, we use it in the conditional, so it marks the conditional as tainted. And then we have also the explicit flow inside the conditional. Oh, and I forgot to say, we use this super secret ACM CCS password from this year in this simple example. But as you see, there's no security violation according to this taint analysis, because it couldn't find the relation between the password and the sink, because it only considers explicit flows. Observable tracking, on the other hand, does something slightly more advanced. When it finds the tainted conditional in the if statement, it then propagates an information flow to every assignment inside the statement. So it will taint the got_it flag and then see the flow to the sink statement. So it would conclude that there's a security violation. But this only if we have the CCS password. If we have something else like the foo constant, then the conditional is evaluated to false. So the if statement, the true branch of the if statement, is not executed. So again, there's no security violation. The more advanced technique that would solve this problem basically would use a security monitor. There are different techniques, but basically once it finds that you are trying to assign something inside a secret context, inside the if statement, the monitor raises a violation, it stops the execution, and a way to prevent this from happening again is to include something that's called an upgrade statement, which basically makes this implicit flow explicit. It says, okay, on every execution, you see that we put it before the if statement, there should be a flow from the padded password to the got_it flag. And then basically every subsequent passes of the analysis would detect the flow both on the true branch and on the if else branch of the analysis. So these are roughly the directions of considering implicit flows and explicit flows in program analysis. You can see that we have from taint analysis to information flow control different design choices. But going always to the right on the heavy side is not always benefic, but that's exactly what we want to check in this work, is what's the trade-off between the benefits and the costs of choosing more and more complex information flow analysis. So on the benefit side, we have the fact that we can reason better about the flows in the program. We have even a more fine-grained of way to analyze the relation between different statements. Hopefully this will lead to detecting more and more vulnerabilities. But on the cost side, we have an additional runtime cost of considering different implicit flows. We have the well-known problem of label creep. This is a state of the analysis in which everything becomes tainted, basically, and then the usefulness of the analysis becomes limited. And the permissiveness, which is the fact that these runtime monitors very often raise a lot of alarms, and it would basically take the attention of the analyst from the security problems into convincing the monitor that certain operations are allowed or not. And in the paper, we have different components. We have basically a dynamic analysis that we built. We propose a set of metrics. We apply the analysis to some benchmarks that we collect from the previous work. We then perform an empirical study, and we have a set of results. We also have the formal semantics of the dynamic analysis and some nice theoretical results, which I invite you to read in the paper. But in today's talk, I will mainly discuss about the metrics, the benchmarks, and the results we have. So the first distinction we have in our analysis is between microflows and source-to-sink flows. So microflows are the flows between different program elements, between variables. Like basically each time a variable becomes tainted, we say that we have a microflow. And we have three types of microflows. We have explicit microflows, which directly assign the taint from B to A. We have observable implicit, which basically are whenever we execute a branch of a secret conditional, and on that branch there is an assignment. And the hidden implicit flow is what we discussed earlier with the upgrade statement, is basically when the fact that you don't execute a specific statement leaks some information about a value in the program. The end-to-end flow or source-to-sink flow, on the other hand, is what security analysts ultimately care about. So basically relations between source and sinks. And these are composed of a sequence of microflows. In this example here, we have one source-to-sink flow from password to got it to the sink call in the last line. And we have two microflows, one explicit microflow in the first line, and inside the if conditional, we have an observable implicit flow. And this is what our dynamic analysis basically counts or observes at runtime. We then discuss the metrics that we propose. So first metric is the label creep ratio. So the label creep was a problem that was previously discussed in the literature, but it was never quantified or formalized in any way. So we propose to measure this by counting the percentage, or by computing the percentage of fields that were ever assigned a sensitive variable out of the total number of fields assignments. And in this simple example here, we have three assignments, and one of them is actually tainted or sensitive. So we have a 33% label creep ratio. On the right side, we have two variables that are tainted, the got it flag and the padded password. So we have a 66% LCR. And this will help us reason about the label creep cost, as you will see later. We also propose using a new metric about the coverage, but that basically gets adapted to our use case of seeing how well we introduce these upgrade statements. And for that, we basically only need to count the conditionals that are tainted. And in this example here, we have two if statements with two conditionals. One checks the got it constant, which is just false here, so it's not tainted, just a constant. And the second if statement checks the padded password, which is a tainted variable. So even though with these two inputs here, foo and super secret password, we have a branch coverage of 75% because we don't cover the else branch of the first conditional, but we have 100% SBC. And you can see that there is a difference between the classical branch coverage and SBC. Now a bit about the implementation. So we build our taint analysis based on Jalangi framework for JavaScript dynamic analysis. We have an expressive policy language that allows us to mark parameter, callbacks, arguments, and so on. We have a set of models, some for the built-in native functions, like for the majority of them, we propagate taint from the argument to the return value. And for some specialized, widely used functions like array push, we have a different model that we wrote. We have a lot of unit tests to show that our dynamic analysis propagates the taint as expected. And a bit about the benchmarks. We have some benchmarks that, as I said, they are aggregated from our related work on server-side vulnerabilities. So we have injection vulnerabilities, regular expression, denial of service vulnerabilities. We have some confidentiality vulnerabilities which we took from the community. So these are things that the Node.js developers reported. And we have a set of client-side leaks which are mostly related to fingerprinting. So these are cross-site leaks about the environment in the browser. We have inputs that trigger both the payload, so the malicious execution, and for increasing the coverage metric I showed you before. And for each benchmark, this is very important, we have our analysis on the heaviest mode. It detects basically a source to sink flow. That means that it would raise a security alarm for the developer. So it would detect it as malicious, that specific input. In total, our study involves 50,000 lines of JavaScript code, 65 upgrades that we automatically add, and our benchmarks have almost 70% average SBC. So this shows that we included a lot of upgrade statements. Now, I'll go to the results part. Basically, I'll start with the benefits. First, about this idea that we get more fine-grained flows. So here I plotted the 56 benchmarks. With blue, we have the explicit flows. With red, the observable implicit, and with yellow, the hidden implicit. As you see, most of the flows are explicit flows, actually. There's a lot of observable implicit, but this hidden implicit caused by not executing branches, they are very limited. And they show up, I think, in 4 or 5 of the benchmarks. But very interestingly, when we looked at the end-to-end flow, so this is all the microflows that we observe in the program, but how do they actually correlate with the source-to-sink flow? So with the things that the security analysts ultimately care about. So remember that we have at least one such flow per benchmark. And as you can see, for the first 3 classes, so the injection, the redos, and the buffer vulnerabilities, we could detect this just by using a taint tracking. So a simple taint analysis that looks at explicit flows could detect those. But for the last class, the fingerprinting ones, which are the confidentiality issues, there we need observable tracking. So basically, we need to look for the implicit flows, the first type of the implicit flows we discussed. However, for the hidden implicit flows, we only found one such source-to-sink flow for one of the redos vulnerabilities. Now, on the cost side, first we discuss permissiveness. Here we compare 2 well-known security monitors proposed in the literature. So basically, on our spectrum, they would be both on the right side, considering both observable and hidden implicit flows. These are NSU and PU. And before, it was speculated that PU is indeed more permissive. Actually, P stands for permissive upgrade. So as we show in this figure, indeed, the PU strategy is way more permissive than NSU. But when you compare this with the source-to-sink flows, which taint analysis or which the analysts ultimately care about, this is both of them produce way more alerts. And for example, for one of the benchmarks, NSU produced even 80 alarms instead of just one that the analyst would care about. The second cost metric we propose is the label creep ratio. And here for each of the benchmark, I plotted on the execution, which we have on the x-axis, the label creep variation, label creep ratio. And as you see, for some of them, indeed, this is a really serious problem. We get to 80% value, so it means that 8 out of 10 variables are actually tainted at the end of the execution. So for those cases, it has indeed, it's very limited, the usage of the analysis. However, the cost is like the average LCR metric is only around 20%. So for the average benchmark, this is not such a serious problem. It's just 1 out of 5 variables are tainted. And now the last cost metric we propose is basically, before that, sorry, even though this LCR metric is not at such high value on average, there are cases like this. So here we have one benchmark and 2 different settings for the analysis. Here we have the taint setting, so we only taint explicit flows, and the upper curve is basically when we consider implicit flows. And as you see, there's quite some difference. So we have 35% difference in this LCR ratio, because as expected, if you consider more implicit flows, you will see more tainted values at runtime. And the last cost metric is the runtime overhead. Here, instead of measuring the actual time, we consider only the number of tainted operations we see at runtime, because we wanted to abstract from our implementation details. We have the 4 types of vulnerabilities we consider, and the 3 settings for the analysis: the taint tracking, observable, and implicit flow. As you see, there's some difference between the last 2, the observable and the implicit flow control, information flow control, sorry. Especially for the redos vulnerabilities, it's almost 20%. The difference. So if you consider more implicit flows, you get more runtime cost. But the big cost is between the taint tracking and the observable tracking, which is a 2.5-fold increase in the number of runtime operations. So to conclude, and in this empirical study, we consider 56 benchmarks that cover different kind of security problems, from integrity, availability to confidentiality. They are mostly non-malicious, so only the last type, the fingerprinting vulnerabilities that we consider assume that the attacker tried to bypass or try to do something, to use these implicit flows in a specific malicious way. The rest are considered to be vulnerabilities introduced by the developers. We propose 2 metrics for evaluating the cost of considering implicit flows and building increasingly complex information flow analysis. We show that implicit flows are very expensive to track, and they have limited value, but they have their place in the security program analysis landscape. When you are looking for confidentiality, or you're shifting towards the malicious mindset, then you definitely need to consider implicit flows. And we show that taint analysis is sufficient for tracking problems in integrity and availability benchmarks. And with this, I'll conclude my talk, and I'll be very happy to take any questions that you may have.
Excellent. Okay, so if anyone has questions, please use the microphone. Yeah.
So this creep metric that you have there,
yeah.
So that's independent of how many variables you need to taint to derive a particular end-to-end flow. So shouldn't we theoretically control or sort of normalize that metric by what's actually necessary for a taint analysis, as opposed to presume that every taint is an over-taint?
Oh, I see. So basically to remove the useful taints from
right, the ones that are actually necessary for the end-to-end.
Yeah, I think that's a great idea, and we should probably refine this metric. So it's just an initial proposal, and it's very coarse-grained, as you correctly point out.
And so how many variables are in these benchmarks? So you said there was cases where everything got tainted, but everything included how much?
Yeah, I don't have those numbers, but as I showed on the slide, it's basically 50,000 lines of code in total. So per benchmark, yeah, there are some that are very simple, and as you're correct, you have the correct intuition that probably for some benchmarks you have 5 variables, and they are all used on the source to sink kind of flow, right?
Okay, thank you.
Thank you.
Go ahead.
Hi, thank you for the talk. Question about handling strings and regex in the way that you do tainting. So let's say you got something that is, you combine something, only one of them is tainted, and I split that up again. How is that tainted?
Mm-hmm. So basically that would hit our default native functions model. So it would propagate everything from the arguments and the base object to the result. And in this case, it would mark the result as tainted.
I see. So if I do join and then split, then everything in the split will be tainted.
Indeed.
I see. Okay. Yeah. Is there any benefit to doing it separately or doing it by index, possibly? Probably massive overhead, by the way, but...
So basically to only mark some of the things in the result array or something like that. Yeah. To be honest, this was the best effort kind of analysis. We included things in the analysis until we found the correct vulnerabilities and that we showed that it's useful for detecting the vulnerabilities. But if you refine the models, then obviously you get less false positives in the end.
I see. Yeah. So I'm suspecting that the ones with the high LCRs seem to be are they regex based, or could you give some intuition on what caused them? I might have missed that part.
I think we can go back to Peter's question. That basically it's a very simple example with very few variables that they are all used and all become tainted, and that's actually not a problem. It's rather a limitation of our LCR metric.
I see. Okay, and so even for the string ones, you got mostly to 20%, as you said, around. I see. Okay, thank you very much.
Thanks.
Okay, let's thank the speaker again.